is the notes for AP Calculus on the topic of parametric equations. So with parametric equations, if we've got two functions f and g that are continuous on some interval, then the equations x equals f of t and y equals g of t are called parametric equations, where t represents the parameter. So what we have here is a function that represents the x-coordinate at a given parameter t, and a function that represents the y-coordinate at a given parameter t. And it doesn't have to be, but usually on these problems, t is representing time. So because of that, we'll usually have an interval that only has positive times. In this case, t is greater than or equal to 0. Particle is moving along a curve, okay, and its position at any time is given by this. So instead of one position function that tells us, let's say, the height of an object or how far it is horizontally away from something, with parametric equations we can represent both two different dimensions of the position. So it's a little more advanced than just a single equation for position, where it's just linear in one direction. So x of t here, at a given time, this tells us what the x-coordinate of the function is. Similarly, y of t at a given time tells us what the y-coordinate of the function is. So let's figure out the x-coordinate and the y-coordinate at a few different times, starting at time 0 going to 3, to see what kind of a graph this would end up looking like. So let's start with time 0. If we substitute in 0 for t, and figure out what x is, well, that's just going to be 0 cubed minus 2 times 0 squared plus 0 minus 3. You can see the 0 wipes out all those terms. All we're left with is the negative 3. So at time 0, the particle starting at an x-coordinate of negative 3. And we can do something similar for the y-coordinate, substitute in 0 for time. You get 0 squared minus 2 times 0 plus 1. Well, zeros wipe everything out but the 1. So negative 3, 1 represents the point where this particle starts at. So let's go ahead and graph it over here. We'll sketch the path of the particle in the xy plane below and indicate the direction of motion. Oops. So we have to clear those off. So we'll start at negative 3, 1 right there. That's where this particle starts at. Let's find at time 1 now what the x and y coordinates are. So x of 1 would be 1 cubed minus 2 times 1 squared plus 1 minus 3. Well, 1 cubed is 1. 1 squared is 1 times negative 2 is negative 2 plus 1 minus 3. So you can see that's 2. 1 plus 1 cancels out with a negative 2, so all we're left with is negative 3. So in this case, x-coordinate stays the same. It's negative 3. Same as it was at time 0. And then at time 1, the y-coordinate would be 1 squared minus 2 times 1 plus 1. 1 squared is 1. 1 times negative 2 is negative 2 plus 1. You can see that just gives you 2 minus 2 is 0. So now the y-coordinate is 0 when the x-coordinate is negative 3. So it goes from negative 3, 1 to negative 3, 0. So right there. And then let's substitute in 2. So if we substitute in 2, that would be 2 cubed minus 2 times 2 squared plus 2 minus 3. So 2 cubed is 8. 2 squared is 4 times negative 2 is negative 8 plus 2 minus 3. So the 8's cancel out. We're just left with 2 minus 3 and negative 1. So now the x-coordinate is negative 1 at time 2. And the y-coordinate at time 2 would be 2 squared minus 2 times 2 plus 1. 2 squared is 4. 2 times negative 2 is negative 4 plus 1. You can see the 4's cancel out. We're just left with 1. So now at time 2, the particle is at the point negative 1, 1. Let's plot that, negative 1, 1 right there. So it went from here to here to here. Strange looking graph so far. All right, now let's substitute in one more time 3. So if we substitute in 3, we'll get 3 cubed minus 2 times 3 squared plus 3 minus 3. Well, 3 cubed is 27. 3 squared is 9 times negative 2, negative 18. You can see the 3 and the negative 3 cancel out, so that just leaves you 27 minus 18, which is 9. So now the x-coordinate at time 3 is 9. And finally, let's find the y-coordinate time 3. Would be 3 squared minus 2 times 3 plus 1. 3 squared is 9. 3 times negative 2, negative 6 plus 1. Well, that gives you 9 minus 6 is 3 plus 1 gives you 4. So at time 3, now the particle is way over at 9, 4. So, it started at negative 3, 1, negative 3, 0, negative 1, 1, and 9, 4. So we know it goes in that order. So when we sketch the graph here, it's a little tricky to tell what's happening. Is it going in a straight line? Is it curving this way or this way? To figure out for sure, you'd have to plug in a time between 0 and 1, like 1/2, and then we can tell exactly what's happening here. What turns out is if you plug in 1/2, you get a point somewhere over here. So it ends up looking like this. And then it curves from there. Like that. And then it keeps going this way. So we plugged in an additional time there. So you can see we've got a cusp right there at negative 3, 0, an abrupt change in the slope. So that'd be the rough sketch of it. And indicate the direction, you just put not just an arrow there, but just an arrow. You can put just one arrow or more than one arrow along the curve to show which way it's going. It's traveling along the curve that way. So here it is. Here's the part at time 0, time 1, time 2, and then time 3. Tells you two different coordinates of the position rather than just a typical position function where it's just one coordinate. Now let's see, if we want to know at time 1/2, is the particle moving to the left or to the right? Okay, and then some kind of a justification. Well, what indicates the left or right motion is what's happening with the x-coordinate. So what we need to know is the x dt, which is like the velocity, the derivative or velocity of the x-coordinate. If it's moving to the left, that velocity of the x-coordinate, or dx dt, is going to be negative, less than 0. If it's moving to the right, in this notation, instead of dx dt, I forgot, it's x, we'd call it x prime of t. Same thing, but just since the original function is written as x of t, the derivative would be x prime of t. Moving to the left, that velocity would be negative. The x-coordinate would be decreasing. And if it's moving to the right, the derivative of the x-coordinate would be positive because the x-coordinate would be increasing. So let's go ahead and find the derivative. X prime of t. The derivative, you can take the derivative of each of these separately. The derivative of t cubed is 3t squared. Derivative of negative 2t squared, bring down the 2 to be negative 4t. The derivative of t is just 1. And the derivative of a constant negative 3, constant by itself, is 0. So now this would give you how the x-coordinate is changing at any time. We want it specifically at time 1/2. So let's go ahead and substitute in 1/2. So 3 times 1/2 squared minus 4 times 1/2 plus 1. 1/2 squared would be 1/4 times 2, so that would be 3/4. That's negative 4 times 1/2 is 2, so plus 1. So you get 3/4. Negative 2 plus 1 is negative 1. So that's 3/4 minus 1 is 4/4, gives you negative 1/4. The key thing we're looking at here is whether it's positive or negative. In this case, we can see it's negative. So, because it's negative, that tells us the particle is moving to the left. So we can say at t equals 1/2. And a lot of times on these Parametric ones, they don't give you any units for time. Sometimes they do. They could be seconds or minutes or something, but this time they don't. So we don't have to put units because they were not any given to us in the problem. Let's say t equals 1/2. The particle is moving to the left since the reason we know is x prime. Now here we don't want to put t because that would be any time. We look specifically at time 1/2 is less than 0. So if we look at our graph, see if that matches up. Time 1/2. Well, 1/2 is somewhere between time 0 and 1. So notice here it's moving to the right, and here it's moving to the left. So it could have been either one of those there, but what we figured out, it's moving to the left, so at time 1/2 must be somewhere down here where it's moving left, as opposed to somewhere up here where it would be moving right. Now, similar question, at this time 1/2, is the particle moving up or down? Well, if you want to know vertical direction, and then we're going to justify our answer here, that has to do with what's happening with the y-coordinate. So we need the derivative, or essentially the velocity of the y-coordinate. So if it's moving up, the derivative or velocity of the y-coordinate would have to be positive or greater than 0. If it's moving down, the derivative or velocity of the y-coordinate would have to be less than 0. So now let's find y prime of t, and we want to look specifically at time 1/2. So the y-coordinate would be 2t minus 2. And again, let's substitute in 1/2 there. That'd be 2 times 1/2 minus 2. That'd be 1 minus 2 gives you negative 1. So, since we got a negative for that, that means the part for the derivative of y at 1/2, that means the particle is moving down. Which, if you think about our graph, does make sense, right? We could see at 1/2 we knew somewhere here, it is heading down as well, as we found it's moving left, so it's somewhere right there. So we can say at t equals 1/2, the particle is moving down since, again, similar justification, it's because the derivative of y, specifically at 1/2, y prime of 1/2, is less than 0. And finally, one more question. It says at what point or points, x, y, so if any, is the particle at rest? Now this phrase, at rest, remember, I think at rest means it's not moving. And if something is not moving, does that tell you something about its position, its velocity, or its acceleration? Well, not moving means the velocity would equal 0. So if this was a normal problem, it would typically just set the velocity function equal to 0. However, on a parametric equation, there's two different velocities, remember? X prime of t is the velocity of the x-coordinate, and y prime of t is the velocity of the y-coordinate. So in order for the particle to not be moving, both of those have to equal 0. So we'd say x prime of t equals 0 and y prime of t equals 0. So that, in order for it to be at rest, there has to be some time that makes both derivatives of the x-coordinate and the y-coordinate both 0. So it's not moving up or down, and it's not moving left or right. So we already have the derivatives in the previous problem. We just have to set those equal to 0 and see if they have any times in common or not. So if we set this first one equal to 0, x prime of t equal to 0, at 3t squared minus 4t plus 1. So for this one, we're looking for factors of, it's quadratic, there's no GCF, factors of 3. The sum is negative 4. Well, what would work there would be negative 3 and negative 1. So since it has a leading coefficient that's not 1, remember what we do is use these two numbers to split up the middle term. So we leave the 3t squared alone and split up the negative 4t into negative 3t and negative 1t. You can see that's the same as negative 4t, and then leave the plus 1 alone. And then remember you split it in half. 4 terms. GCF of the first 2 terms would be 3t. And that would leave you with t minus 1. GCF of the last 2 terms, since this is negative, would have to be a negative 1. And when you take out the negative 1, notice that changes this to a positive t and a negative 1. So that does match up as t minus 1. So now you can take out a GCF of t minus 1, which they both have. And then what would be left would be 3t minus 1. So now it's equal to 0. The only way these can multiply to be 0, one of them is 0. So either the t minus 1 would equal 0, or the 3t minus 1 would equal 0. So if you solve this one, you get t equals 1. Here, add the 1 divided by 3. So t equals 1/3. So there's 2 different times in which the x-coordinate is basically at rest, or the x-coordinate's not changing at time 1/3 and time 1. But now let's look at the y-coordinate and set y prime of t equal to 0. So y prime of t, remember, was 2t minus 2. So if you solve that one, you can either factor out of 2 or add 2 divided by 2. Either way, 2 can't be 0. That gives you t equals 1. So at time 1, notice that's the one they have in common. Both x prime of t and y prime of t is 0. So that would be the time it's at rest. Time 1/3, only the x-coordinate's at rest. Okay. So normally what you would do, because we want the point or points, you would find now the position at time 1 of the x-coordinate and the position of time 1 of the y-coordinate. But notice we already did that. We got, it was negative 3 and 0. So that's the point we're looking for, being negative 3 is 0. We can see that on our graph that we've graphed here. Negative 3, 0 is right there. So let's think about the answers we got. Well, you can see there, see how it's transitioning there? It's making a sharp turn. So for just an instant, the x-coordinate and y-coordinate, it's at particles at rest, are not changing there. And notice we got another time of 1/3, whoops, for just the x-coordinate. And the reason why we got that, time of 1/3, remember we saw time 1/2 right here was somewhere down here on the graph because it was moving left and down. So now I know time 1/3 must be exactly right there, right where it's changing from going right to going left. And that's why for one instant there, the x-coordinate is not changing because it's transitioning from moving right to moving left. However, the reason why it's not at rest is because notice it's still going down that whole time. So the y-coordinate is still changing, so that's why dy dt is not 0 there. As opposed to this one, both the x-coordinate and the y-coordinate change because it goes going left, it has to switch to go right, and it's heading down, and now it's heading up. So that's why it occurs at the point negative 3, 0. Now let's take a look at one more example, just slightly different. On this one, we've got same thing except 2 different functions. And notice they won't always be written in function notation. Sometimes it's just x equals and y equals. That's fine. So let's again figure out the x and y coordinates. Starting at time 0, going to time 3. So if we plug in 0 for t, well, if we plug in 0 here, wipes out everything but the 3. So the x-coordinate this time starts at 3. And for the y-coordinate, Notice what happens here, we get an imaginary number. So this does not exist. Doesn't happen very often. So we're not going to see anything on the graph at time 0. Even though it says time greater than or equal to 0, it's not there because we got an imaginary number. So let's try time 1. Let's see, that's 1 minus 4 plus 3, so that's 3 plus 1 is 4 minus 4, so that gives you 0. So at time 1, the x-coordinate is 0. And the y-coordinate, notice once we plug in 1, now we get the square root of 0. That's the first number that's not going to give us, if we plugged anything between 0 and 1, notice that would also be imaginary. So you plug in 1, that gives you 0, square root of 0, cubed, the square root of 0 is 0, cubed gives you 0. So this point, at 1, 1, that's the first point we actually have, starts at the origin, 0, 0. All right. Now let's go ahead and substitute in 2. That'll be 2 squared minus 4 times 2 plus 3. Well, that's 4 minus 8 plus 3. Let's see, that's 4 plus 3 is 7. Minus 8 gives you negative 1. Now the x-coordinate is negative 1. And then the y-coordinate, that'd be the square root of 1, which is 1 cubed gives you 1. So negative 1, 1. Here's our next point. Right there. And finally, let's substitute in 3. So 3 squared is 9. 4 times 3, 12, plus 3. Gives you 9 plus 3 is 12, minus 12, back to 0 again. And let's go ahead and substitute in 3 here. So we get the square root of 2 cubed. So here to figure out what this is, that's exactly what it is. To give us an approximation to help us graph it, though, if we switch this to radical form, this would be 2 to the 3 halves, right? Or 3 halves is the same as 1 and 1 half. So to figure out what this is between, well, we know 2 to the first is 2, right? And we know 2 to the second is 4. So we know it's somewhere between 2 and 4. I'll estimate around 3. Okay. So this one we can see. Particles going like this, based on what we can see so far. We have to find some more points to see exactly what it looks like beyond that. And we can indicate the direction of the particles moving with arrows. Again, we want to know, is the particle moving left or right? So that has to do with the derivative of the x-coordinate, which in this case we'd write as dx dt. This is just x equals, it's not function notation. We want to know at time 3. So dx dt would equal derivative of t squared minus 4t plus 3 would just be 2t minus 4. And then we substitute in 3. So you'd write dx dt specifically at t equals 3 would be 2 times 3 minus 4. So that's 6 minus 4, which is 2. So since that's positive, that tells us the particle is moving to the right. So I can say at t equals 3, the particle is moving right, and it'd be since the derivative of x, or its velocity of the x-coordinate, dx dt, specifically at t equals 3 is greater than 0. And now let's find at that same time, 3 is the particle moving up or down. Up or down, that has to deal with the y-coordinate. So this time we're going to have to look at dy dt. So this time let's rewrite y, so it's a little easier to take the derivative of. Instead of t minus 1 cubed, that's the same as t minus 1 to the 3 halves. So when we take the derivative of that, dy dt, using the power and chain rule, it'd be 3 halves t minus 1 to the 1 half times the derivative of the inside, but in this case the derivative of the inside function is just 1, so it doesn't change it. Let me simplify that. dy dt is 3 halves. If you put it back in Rational form, that's the square root of t minus 1. If we plug in 3, three halves times the square root of 3 minus 2. And here, even though this doesn't work, actually that's 3 minus 1, sorry. A little ahead of myself there. So that's the square root of 2, so 3 halves times the square root of 2. This time we don't really have to estimate what it is because we can tell that's positive, greater than 0. So we can say at t equals 3, particle is moving up, and the reason would be since dy dt, specifically at time equals 3, is greater than 0. And finally, at what point, if any, is the particle at rest? Again, at rest means, in this case, both dx dt and dy dt, both velocities have to be 0 for it to be at rest. So we already have their derivatives. So if we set 2t minus 4 equal to 0, set factor out the 2 or add the 4 and divide by 2. Either way, this one's at t equals 2. Oops. And if we set dy dt equal to 0, that was the 3 halves square root of t minus 1. Let's see, 3 halves will never be 0. The only thing that will make this 0 is if what's inside the square root is 0. So t minus 1 equals 0 gives you t equals 1. So notice there's no times that they have in common. So the particle is never at rest. Let's see if this makes sense with our graph. At time 2, dx dt is 0, and at time 1, dy dt is 0. So time 1, dx dt is 0, switching direction there. And at time 2, sorry, time, this was time 1, sorry, time 1, dy dt was 0 because it's switching to be a positive going up, and then at time 2 right here, that's where dx dt was 0 because it's switching from going left to going right. And that concludes the notes for AP Calculus on the topic of parametric equations.